Okay, so next chapter then is electrical power. So general overview of the system. It's a DC aeroplane. So we have 4 engine-driven generators that produce 28 volts, and each one can handle a load of up to 400 amps continuously. We have an APU generator, also producing 28 volts, and can with the same rating, so it can handle up to 400 hertz continuously. Some aircraft, some of the older aircraft, have a AC system. There's only 2 systems that need AC on these older aeroplanes. That's TCAS and GPWS. So in order to provide the AC power that they need, there's a single static inverter. But some years ago there was a service bulletin that came out that removed that static inverter, and TCAS and GPWS are now powered off the DC system. Okay, so you may come across aircraft still that have got an AC inverter. But what we'll do is we'll head over now to the PowerPoints and we'll go through it. So what we have then is predominantly a DC system comprising of 4 engine-driven generators that can produce 28 volt DC, 400 amps continuous load. We have an APU generator producing 28 volts and 400 amps continuous. We also have 2 NiCad batteries. We also have a lead acid battery, which is the backup battery, which has a very specific purpose. It's there to provide power for the generator control units only. So if everything else is going haywire, the GCUs have a stable power supply so they can provide their overcurrent protection. These generators are identified if you stand at the back of the aircraft, look forward. Number 1, left-hand engine on the outboard side. Number 3 on the left engine inboard side. Then you have on the other engine number 2 on the inboard, number 4 on the outboard, plus of course the APU. Each one is controlled by its own generator control unit. There are some basic ground rules that the electrical power distribution logic follows, and the main ones are listed here. So number 1, the batteries cannot be charged from the GPU. You have to have either the APU generator or one of the engine generators running for the battery to receive a charging current. And the reason for this is there is in fact no battery charger per se. The batteries would just draw whatever the source can throw at it. Secondly, GPU has priority over any generator. So if the GPU is online, none of the other generators will come online. The number 2 battery is always used for APU start. On the ground, when you turn the batteries on, what you really need to do is either get ground power on or start the APU, because on the ground the batteries will only last 10 minutes. In flight it's different. If you're down to battery power in flight, the system will reconfigure all the buzzes and it will extend that life to 45 minutes. We'll look at that a bit later on. As previously mentioned, the backup battery only provides power for the GCU. It doesn't feed onto any of the aircraft buzzes. And all the control and all the load shedding is fully automatic. The crew have got some override capabilities, but generally speaking, the crew don't need to worry at all. The system sorts itself out and makes the best use and configures all the buzzes to make the best use of whatever power is available. So what this schematic shows is the configuration as you would find it in a normal situation in flight. So the aircraft's in flight, 4 generators running, the APU is not running. You can run the APU in flight and you can have a generator online, but that is not normal. So this is a normal position for flight. And what you can see is a whole series and network of buzzes. So starting at the top left, we've got the number 1 DC buzz. They're fed from the number 1 and number 3 generators. Coming down from there, if you follow the line down to the bottom, you'll see the number 1 DC buzz provides power to the number 1 shed buzz, and there's a shed buzz contactor that allows that shed buzz to be isolated. The second line along, there's a fuse, and a line comes down via the essential buzz contactor, number 1, and feeds power onto the essential bus. So that essential bus contactor, that's the normal position for that contactor. So the essential bus is being powered from the DC bus, DC bus 1. Then you have another line, the third line, coming down, protected by a fuse and a battery contactor, feeding power onto the hot battery bus, which will then provide the charging current from the number 1 battery. Moving across, going back to the top and moving across to the central DC bus, there's no consumers on the central DC bus. The only thing on the central DC bus is the APU, so the APU generator and the start contactor. That's linked to the number 1 DC bus by the number 1 bus tie contactor, which is normally open. So from the central bus going across, it comes along to the number 2 bus, and then the number 2 DC bus, and the link between the central bus and the number 2 bus is via the number 2 bus tie contactor, which is normally closed as it's shown in the picture. Then coming down from the number 2 DC bus on the far right, so similar how the number 1 system was working, you got the number 2 shed bus, and that can be isolated by the number 2 shed bus contactor. And then you've got from the number 2 bus a fuse comes down via the number 2 essential bus contactor to the number 2 essential bus. The number 2 battery, you'll notice you have a battery 2 contactor, and that feeds up directly onto the central bus. There's also a backup essential bus and a backup hot bus, and then the backup battery. And there's a diode there, so you can see that the backup battery cannot feed back onto the main aircraft buses. And the backup essential bus, there's 2 sub buses coming off of that, the number 1 backup bus and the number 2 backup bus. Now what we'll do a bit later on is go through various failure scenarios, and we'll see how the system configures itself. Okay, so taking a quick look at locations then, obviously the generators are mounted on the engines, the APU generators on the APU. Most of the other electrical components are in the cockpit area or the front part of the aeroplane. So the 2 main batteries located on the nose left-hand side, there's an access panel on the outside of the aeroplane, very easy to access, although be careful, they're heavy. The inverter, if it's fitted, to access that, it's up in through the nose undercarriage compartment, and on the sidewall on the left-hand side there's an access panel. You take that off, and there it is. And sort of almost opposite that, on the other side of the sidewall, inside the nose bay, is the backup battery. Generator control units, the APU GCU is under the cockpit floor. There's an access panel you take off just behind and between the 2 crew seats. The generator control units 1, 3, 2 and 4, they're on the left and right hand side respectively. Access through the side console panels. So they're not under the floor as such, they're at floor level, but they're tucked inside the side consoles. We also have the two main distribution boxes, so that's the left and right power distribution boxes where most of the relays are in terms of the electrical control, like the battery contactors and the bus tie contactors and so on. You'll find those behind the crew seats, and there's also some circuit breakers on there as well. So 2 generators mounted on the engine gearbox. They're air cooled, so there's a NACA scoop on the bottom of the engine intake and an exhaust duct outlet for the cooling air outflow coming out of the bottom of the engine nacelle. When the aircraft's stationary, obviously you've got no forward airflow, so the generators actually have a built-in cooling fan that draws air across them and cools them down. So behind the captain's seat you'll find the maintenance panel. There's a whole bunch of test switches on there which test out individual systems, and we'll go through them when we do the individual system. But you'll see on there's an electrical power switch. It's got 3 positions, a middle position, a test, and a reset position. So the test position, when you go to the test position, it generates or simulates an overcurrent situation. Now in the system, when there's an overcurrent, the generator control unit will take the generator offline and isolate the bus bar by operating a relay which latches. So if they've had an overcurrent event, then what they need to do is reset all the latches. So when the aircraft comes back and has a maintenance team on it, there's a reset switch there where you can set all the overcurrent relays. So generator control units, you access it through the side consoles for the main generator, for the main engine generators, the APU ones under the cockpit floor between the crew seats just behind it. What you have on there is for each generator there's a test jack for you can put a voltmeter on there and look at the voltage, and there's also a little cover screw which you take off, gives you access to a little screw where you can make adjustments to the voltage. If you're installing a new generator GCU, that's one of the things you need to check, and if you need to adjust the voltage, you can just adjust a little screw. That's the only adjustment you can make on it. You don't make any adjustments for the load sharing or anything like that. Right, here is the electrical control panel where the pilots use to control the entire electrical system. We'll start at the top left hand side. So up at the top you have a row of switches. These are the generator switches. When the button is pushed in, you hand over control of the generator to the GCU, and if the GCU is happy that the quality of the electrical power is good and everything is within limits, the generator will come online. If you want to turn the generator offline, you push the switch and release it, you get a white stripe bar in the switch. Also notice how the generators are labelled, so it goes generator 1 and 3 and 2 and 4, which mimics the actual positions of the generators on the engines. So 1 and 3 on the left engine, 2 and 4 on the right. Moving down from there, you've got the GPU switch. When the GPU is plugged in and is ready, you get a GPU available. If you want to turn the generator GPU online, you push a switch, the GPU available light disappears, and a white stripe bar is presented. You do need to make sure that when you put the GPU online, that the GPU available light disappears and you get a white stripe bar. If it doesn't, it means you're still running on battery power. Then you've got the APU generator. Similar logic really to the engine generators. So you push the switch in and the generator comes online if the APU GCU is happy. Release the switch, white stripe bar if it's not. 2 battery switches coming down, battery 1 off and auto. So when it's in the auto position, the battery contactors are controlled by the logic. And as long as the logic is happy, the battery contactors will close. Same with the battery 2. The essential power switches is a guardian switch. What that does, it forces the electrical system to go into an electrical emergency configuration if you lose all 4 generators plus the APU generator in flight. That is a definition of an electrical emergency. The system should configure itself automatically, but if it doesn't, the crew can force it to do that by pushing that switch, and you get a white stripe bar when it's selected. Buzz tie switches, so you have 2 buzz ties, well you have 1 buzz tie switch actually, so the one on the left where it says buzz ties, that's controlling buzz ties 1 and 2. Normally they're in the open auto position, so buzz tie 1 would normally be open, buzz tie 2 would normally be closed. But as we'll see when we go through all the failure scenarios, they do sort of sometimes buzz tie 2 opens, sometimes buzz tie 1 closes, sometimes they're both closed, and in a certain configuration they're both open. So that's controlled automatically. Off means they're both open, you force them both open, and override, you force them both closed. But the override is a bit of caveat attached to that. Although the override position pushes them both closed, they will not close if there's an overload or an overcurrent situation. So always the safety has priority over what the pilot's trying to do. The other rotary switch, off, auto and override, is for the shed buzzes. So this controls the two shed buzz contactors. So in the auto position, they're normally closed as long as you've got two generators online. As we go through the failure scenarios, we'll see what happens to the shed buzzes. You can override it to force it both closed, but again, you can't force it both closed in flight unless you have sufficient number of generators. On the ground, though, it is allowed. And the reason for that, on the ground, potentially you might have just the APU generator running initially. In that situation, the normal logic would be that the shed buzzes would not be powered. The shed buzzes are not powered with a single generator. But on the ground, you can override it. And that means you can get power to the galley and for the taxi lights, for example. Bottom row of push button switches. So you have an AC power switch if you've got the AC system. Some aircraft don't have it, so that area is blank, the switch is removed. That turns on the static converter. The backup switch, when it's pushed in, provides power to the backup battery and provides a charging current to the backup battery. And then the two avionics masters switches, which are normally on. So some avionics kit is powered through the avionics master buzzes, and the avionics master switches have to be on for that. Just a point, actually, it's good practice if the aircraft's in the hangar and it's on maintenance and you don't need all the avionics kit powered, it's good practice to turn off the avionics masters. That keeps the avionic heat that's generated by the avionics units to a minimum. So it's just generally a good idea. So that's the electrical control panel. Here is the APU generator. The reason I've put this picture here, although we said that it's the same rating as the engine generators, i.e. 28 volts, 400 amps continuous, it isn't physically the same generator. The APU generator is in fact a starter generator. So it acts as a starter motor as well to start the APU. And the engine generators are brushless machines. The APU generator has brushes which wear out, and periodically the brushes need to be checked for wear. And you can see in the bottom left picture there how the brushes wear, and there's a wear indicator on them. You can replace the brushes in theory. You can do it on wing. In actual fact, you can replace the brushes. However, in reality, that's not going to happen because the brushes, if you fit new brushes, the brushes have to be bedded in on a machine. So in reality, I know a lot of operators actually that when the generator brush wear task is called up in the maintenance program, actually they just don't bother and rather they replace a generator. It's just as quick to replace a generator as it is to check the brushes for wear, only discover they're worn, and then you have to replace a generator. So a lot of operators just say, okay, sod it, we'll just replace the generator when that's due. Here is the MFD electrical page synoptics, which you can bring up. So what this shows is for each generator it shows the voltage output and the current output. For the GPU it just displays voltage. Then for the batteries it displays voltage and temperature. So for the current output on the generators, anything below 400 amps is okay. We can handle a 400 amp load continuously, so it's in green. As it goes above 400 amps, the figures will change to amber. And actually at that time you'll get a generator overload message when it goes above 400 amps. Doesn't necessarily mean the generator trips off because there's some timing logic that goes on. So between 400 and 600 amps it's allowed to overload for 5 minutes, and if it goes more than 600 amps up to 800 amps it's about 10 seconds if I remember rightly. Then it trips off. Anything above 800 amps it will trip off immediately. But during an overload condition, none of the buzzes will tie together. The APU generator is similar, but the timings are slightly different. So it's something like 2 minutes and 5 seconds for the 400 to 600 amps, and then 600 to 800 amps, and then it trips offline. But as it goes above 400 amps, then for all of them, you'll get a generator overload message. It's quite common to see an APU generator overload message after you've started the APU on batteries, because it takes a bit of a hammering. The battery takes a bit of a hammering during APU start, and so there's an initial surge of current as it tops itself up, and potentially the APU generator goes overloaded. It doesn't trip off, but it's worth just letting it all settle down until the generator is no longer overloaded before you start doing other things with it. A ground power receptacle, then you'll find it on the nose left-hand side, the small access panel that's highlighted there. You open that up, that's the DC ground power input. Also, that's the point where you can plug in a headset, talk to the crew, and you'll find a little indicator there that says GPU available when it's plugged in. And there's also a parking brake on indicator in that switch as well. It looks exactly like a switch, but it's not. It's just purely an indicator, so pushing that switch has no effect on, turning ground power on or whatever. Just forward of that panel, the large square panel, that's the battery compartment, and we'll look at that on the next slide. So this is where the two main batteries are. You open up the big square panel, the one that's in front of where the ground power is, and you'll see the two main batteries there right in front of you, very easily accessible. But I would advise you put some sort of a lifting platform and slide the batteries out, because they're extremely heavy. Just underneath the battery, where the battery tray is, or mounted, you'll find the number 1 battery relay box, with some circuit breakers on there for the shed buzzer, for the hot buzzers. And then just tucked away out of view, just to the right of the number 2 battery, is a number 2 battery relay box. And again, there's some circuit breakers on there for the number 2 hot buzz. So what I want to point out on here is just the fact that each battery has 2 temperature sensors inside it. Obviously, we saw earlier that the temperature is one of the things that is displayed on the MFD when we bring up the synoptic page for the electrical system. And this is where the information is coming from. Now, the indication is actually provided only from a single sensor, the second one. The other thing that we use the sensors for is to provide an overtemp warning message when the temperature of the battery goes above 71 degrees C. Either of those sensors will provide that indication, and the CMC will monitor each sensor to see if it's failed. So if the second sensor fails, the crew will spot it, because they'll lose the temperature indication. But if the first sensor fails, really it's invisible to the crew and is only presented as a maintenance message. This is the backup battery. It's located in the nose undercarriage bay in the sidewall. You take off a little access panel that we've got removed here, and you can see it. So on the lead acid battery, it contains cells. So each of the cells has a LED failure indicator. They're the LEDs at the top of the battery, and then there's 4 LEDs underneath. They're voltage level indicators, and the voltage level will be displayed when you operate the test switch. There's a test switch on the battery itself, and that will indicate the voltage level. The battery itself also has a heater mat surrounding it that's turned on and off if it gets too cold. And when you operate the test switch, you put a load through the heater, so you're testing the battery and the resulting voltage indication when it's under a load condition. The backup battery, remember, just provides a stable power supply for the generator control units, so that they can do their overcurrent protection when everything else might be going haywire. The static inverter, if you have it, is also located in the nose undercarriage bay on the left-hand side, accessed through a similar sort of panel to the lead acid one, on the side wall of the nose gear bay. That provides 115 volts AC for two components, the TCAS and the GPWS. It's powered, or it receives 28 volts input from the number one DC bus, changes that 28 volts to 115 volts single phase output onto the AC bus. As I say, there's only two things on the AC bus, and that's the TCAS GPWS. Operated, turned on by the AC power switch, which is on the electrical panel. And because it's power from the DC bus, we do lose that in an electrical emergency, as we'll see a bit later on. As I said, later aircraft have modification, and this has been removed entirely. The switch is removed and is blanked off, and the TCAS and GPWS get power from the normal DC buses. This is the circuit breaker map for the overhead panel circuit breakers, which I guess you can say are the main circuit breakers. There are other circuit breaker panels, so there's two on the distribution, left and right distribution boxes behind the crew seat. There's circuit breakers on the battery relay boxes, but the main one's on the overhead panel. And as you can see, all the circuit breakers are grouped in bus bars, laid out in grouped together in terms of bus bars. And there's a grid reference system with alphabet and a number to give you a grid reference for each circuit breaker. And also each circuit breaker has got a label attached, so you know what system it's from. And as well as grouping the circuit breakers in terms of their bus bars, they also group circuit breakers in terms of systems as well. But as a lot of systems use multiple power supplies from different bus bars, you do find that with a system, if you took the fuel system, for example, actually a good example would be the fuel pumps. You have 6 fuel pumps altogether, using basically pretty much all the bus bars, the number 1, number 2 DC, and the number 1, number 2 essential. So you find the circuit breakers for the fuel pumps, they appear to be scattered randomly, but they're not. They're grouped together in circuit breakers, and then within that circuit breaker, they group together in bus bars, and then within that bus bar they group together as within a system. What we're going to do now then is go through the various failure scenarios. So this first slide shows all generators online, as you would expect to find in flight, with the APU not running, which is perfectly normal. And as we can see here, so generators 1 and 3 feed in DC bus 1. Generators 2 and 4 feed in DC bus 2. Going along the top line, bus tie contactor 1 is open. Bus tie 2 contactor is closed, allowing the number 2 DC bus to feed the central bus. The number 1 DC bus feeds down onto the number 1 shed bus via the shed bus 1 contactor, and from the number 1 bus DC bus down to the number 1 essential bus via the essential bus contactor. Battery contactor 1 is closed, allowing the power from DC bus 1 to feed down onto the number 1 hot bus and provide a charging current for the number 1 battery. On the other side, number 2 bus, DC bus feeds the number 2 shed bus via number 2 shed bus contactor, and from the number 2 bus down to the number 2 essential bus via the number 2 essential bus contactor. Battery contactor 2 is closed, which allows power from the central bus, which is being fed from the DC bus, to feed down onto the number 2 hot bus and charge up the number 2 battery. You'll also notice at the bottom the number 1, number 2 essential buses, they're connected or potentially connected together. They're not connected currently, but there's an essential interconnection contactor that's open. So effectively we've got 2 networks, a left-hand side and a right-hand side, and they're separated because the number 1 bus tie contactor is open. The next scenario we'd look at then is if we have a failure of a generator. It actually doesn't matter what generator fails in this situation, but we're going to pick the number 1 generator has failed. So we've got the number 3 generator feeding the left-hand side on its own, 2 and 4 generators feeding the other side, working quite happily. So to try and help out the number 3 generator and to share the loads more evenly, we want to form a single network. And we do that by closing the number 1 bus tie contactor. which it does, as you can see from here. So now those 3 remaining generators are just feeding the entire network. We haven't lost any services. Everything is good. The crew now do have the option, if they wanted to start the APU. So if we start the APU and get the APU generator online, then we've now got 4 generators. So the system says, okay, that's good. We can now form 2 networks. So what we need to do is couple the number 3 generator and the APU generator together on a single network. And then we have the number 2 and 4 generators operating the other network. And the only way we can do that is to keep the number 1 bus tie contactor closed, but open up the number 2 bus tie contactor. So now we've got the number 3 and the APU on one side, 2 and 4 on the other. So we've got 4 generators back online again. Okay, happy days. So following on from there, we're going to go to a situation where we lose 2 generators. We'll go back to the situation where the APU is not running. So we lose 2 generators. Obviously, the system has to form a single network. So bus tie 1 will close. And at this stage, we're going to have to start shedding some loads. So the first loads to shed are the completely non-essential loads. So that's all the loads on the shed buses themselves. So things like the galley equipment, that sort of thing, totally non-essential. So shed buses 1 and 2 contactors will open, shedding those loads. Okay, nothing happens to the bus tie contactors, they're both still closed. And the 2 generators that are left are feeding the entire network. No problem at all. The crew again have the option, if they want to start the APU. So the APU is started, generator comes online, APU generator comes online. We've now got 3 generators running. Now in terms of, we can't form 2 networks because we've only got 3 generators. We can't share the load, evenly with only 3 generators, because you'd have 2 on one side and 1 on the other. So the bus tie contactors remain closed. But because we've got 3 generators now, we allow us to regain the shed bus contactors, or the shed buses, so they will come back online automatically. So both shed bus contactors will close, and so we regain all our services. Okay, take it a step further. We now lose 3 generators. Okay, no APU at this stage. We lose 3 generators, so obviously we've only got 1 generator left. He's working his little socks off, so we have to close bus tie 1 to form a single network. So that's closed. We've only got 1 generator, so there's no way we can have the shed buses online. So they will both be offline. They will go offline. Shed bus contactors will open. But again, we haven't lost any of our major services. We've only lost the sheds. Again, the crew do have the option to start the APU. But if we start the APU, that still only gives us 2 generators. So that's not enough to regain the shed buses. So they still will remain off. So we don't really gain anything by starting the APU, but at least we've got 2 generators. The next scenario is we lose everything. This is the definition of an electrical emergency. And we can only have an electrical emergency in flight. But if we lose all 4 generators, there is literally nothing other than the batteries to supply power. So we have really got to shed the loads. So bus tie 1 will open, bus tie 2 will open. Normally the number 1 and the number 2 essential buses are powered from the number 1 and number 2 DC buses respectively. There is no power on the number 1 and 2 DC buses now, so we've got to get power to the essential bus from the batteries. So the number 1, number 2 essential bus contactors change over, and connect to the number 1 hot bus and the number 2 hot bus respectively. The battery contactors, so currently the battery contactor previously was closed, and that would allow the battery to feed the DC bus 1, which is no good. So battery contactor 1 will open. Now battery contactor 2 is a little bit different. Battery contactor 2 actually remains closed and allows the battery to feed up onto the central bus. But there are no consumers on the central bus other than the APU. And definitely we might want to start the APU. So we need power on the central bus if we want to start the APU. So we've got the number 2 battery contactor remains closed and feeds up onto the central bus. Obviously, to stop the central bus feeding the number 2 bus, the number 2 bus tie contactor opens, as we said a little bit earlier on. Obviously, shed buses are offline. And to make the 2 batteries share the load evenly, the essential interconnection contactor will now close, linking the number 1 and number 2 essential buses together to allow them to the 2 batteries to work in parallel and share the loads. And in that situation, the batteries will last about 45 minutes because we're only down to essential loads now. So we pretty much lose half our comms equipment, we lose half our nav equipment, we lose all the display screens apart from ICAS, and the only other thing we've got is the RMU. If we start the APU, and I haven't got a slide that shows this, but if we started the APU, basically everything comes back online. It's happy days again, apart from, of course, the sheds. Okay, going to the next scenario, which is basically GPU, which obviously only happens on the ground, but if the GPU is powering everything, as far as this Embraer is concerned, it's free power, so everything is powered, including the sheds. The only slight difference is, remember the rule, the batteries cannot be charged on the GPU, so to stop that from happening, the number 1 and number 2 battery contactors will be forced open, which stops the GPU from trying to charge the battery. And finally, this last slide shows the situation with only the APU running, but on the ground, because you'll notice that the shed buses are online. The only way we can achieve that with a single generator is if we're on the ground, and if we've turned the override switch, that's a shed bus override switch, to the override position. And that allows us the single generator. Normally you need 3 generators, remember, any 3 generators to power the sheds, but on the ground it does allow us to override it. So they switch the switch to override and allows the APU to feed everything, including the shed bus, including charging up the batteries. Okay, so that was the electrical system in a sort of summary, in a nutshell really. Now, in the last few minutes of the video, I was going through all the failure scenarios. I just want to point out once again that all of this logic is entirely automatic. The crew don't need to do anything. They just leave everything as it is and the system sorts itself out. Now, the other thing to highlight here as well is that there's no computer doing this. There's not a digital control system. All of this logic with all these contactors opening, closing, depending on which generator's online, it's all entirely done by wiring logic and relays. So in the distribution boxes, the left and right distribution units, you'll find a whole bunch of all these relays that we were highlighting on the screen there about the bus tie contactors, the shed bus contactors, the battery contactors, the essential interconnection contactor. All of those are in the left and right distribution units. And it's just through the wiring logic that automatic logic manifests itself. Okay, so that's the end of electrics. Hope you're still awake. We'll head over now to the next subject.